it is going to be huge. As I said in my own talk, the emergence of the mechanical bond is a once-in-the-blue moon situation in chemistry, because this is a new bond that is as strong, as weak, however you want to put it, as the weakest covalent bond in the molecule. And so we now have another bond that brings with it a huge number of new opportunities within chemistry. It's revolutionizing stereochemistry. We don't need to depend on so-called stereogenic or chiral centers anymore. We can use, in the words of Vladimir Prelog, axial chirality, planar chirality, even helical chirality to aid and abet things like asymmetric synthesis, asymmetric catalysis, and so forth. So chemistry is going to have a huge big fill-up from the advent of the mechanical bond. And then another part of chemistry, and that relates more maybe to knots than to catenanes and retaxanes, is chemical topology. I mean, the surface is only being scratched at the moment, and the fact that people are going to be able to wrap chains up into knots of all kinds of exotic conformations means that we are, following there in the footsteps of nature. Nature has done this, and so there's no reason why we can't, in that case, follow. Although I would come back and say, as far as the mechanically interlocked bonds are concerned, we've developed our understanding of those and our ability to be able to make them at the same time as the biologists and other people in the biomedical field began to appreciate that, yes, they're commonplace in biology as well. I was never very hot on chemical reactions, other than they were a means to an end. So I guess I have to go and seek refuge in the Williamson ether synthesis, which delivered the Crown ethers. That's one of my favorites. In a more modern context, Barry Sharpless, and though he wasn't the only inventor of it, his click reaction with the azide reacting in a electrocyclic manner with the alkynes. That's another, I think, very beautiful reaction from the point of view of what I'm trying to do, that is make molecular machinery. Yeah, the world is replete with good examples of reactions, but as I emphasized this morning, it's only once in a blue moon that a new bond comes along, yeah? I have to say to them, just as I had, you will be serving most likely a period of 10,000 hours, which equates with 10 years, being the apprentice, learning the tools of the trade, and at the same time reading profusely about science in general, so that if at the end of that period you step into an academic position or into a good position in a research institute or at one time in an industrial laboratory, you can make a determined effort to do your own thing. It is not too difficult to do your own thing. You've got to identify something that has been languishing in the sort of scientific scene. There'll be nothing that's new. There are no firsts in science. There will have been people there before you, but they won't have made very much progress because the techniques will not have been available to characterize what they did or the ways in which they carried out their approach. In the case of the mechanical bond, Jean-Pierre Sauvage talked about the wonderful work of Gottfried Schill in Freiburg in Germany. But, it was 20-odd steps in synthesis to get to that, whereas Jean-Pierre was able to come up with virtually a one-step synthesis. And so that's what makes the difference, the sheer elegance of being able to do something easily and quickly. So, I think young people have a great opportunity to build on where we are in chemistry today. Chemistry has undergone a revolution in my lifetime. It now interacts with all the other disciplines as equals, whereas when I started out we were all in silos and we weren't supposed to speak to people. And the whole atmosphere now, the whole openness to ideas and discussions with people from cognate scientific communities and engineering is conducive to allowing people to do absolutely amazing things. I have my co-author on Nature of Mechanical Bond. Carson Bruns, and he's at the University of Colorado, and he's doing his own thing. I mean, he's been on a TED show recently. I always saw, he's covered in tattoos. Have you heard this story? And he's now telling us that these can be used. These tattoos not to be dumb based on just carbon particles, but based on smart particles. And so you can read your temperature, you can read your blood glucose, you can maybe, if you have a pacemaker attached to your heart, you can maybe charge it without surgery coming into the scene. So, I mean, that's a good, I think, example of what happens when you tell a young person who's been with you, go out there and do your own thing. Full marks to Carson.